All right, so no burning questions yet? All right, so we kind of flew through an induction example at the end of Friday's class. So I want to go through that more carefully because, again, it's an example of a proof that also leads to an algorithm, which is going to be a theme we bump into more and more. So let's do another postage stamp example. And I'll do the one that I started to do on Friday and then changed my mind, but it's actually not a bad one to do. So prove you can make any postage. And let's see, how much postage are we going to require? Greater than or equal to 9 cents. Using only 5-cent and 3-cent stamps. All right, so you've got an unlimited supply of 3-cent stamps and 5-cent stamps, and you want to show that for any number bigger than or equal to 9, you can find a combination of 3s and 5s that gets you to that number, basically. So we could make this very mathematical, right? We could solve the equation n equals 5x plus 3y, where n is bigger than or equal to 9. But let's keep it informal and just talk about this in plain words and see how we can use induction to do the rigorous part. So we need a proposition. So let P of n be the proposition n cents can be made with 5-cent and 3-cent stamps. Can be made meaning we can make that exact postage. So assume P of n. Well, first we need a base case. So P of 9 says we can make 9 cents postage using 3-cent and 5-cent stamps, and that's obviously true. We can use 3 3-cent stamps. So that's true. So now let's assume P of n, where n is bigger than or equal to 9, and our goal is to prove P of n plus 1. Okay, that's all we got to do. Then we can say mathematical induction gives us P of n for all n. So as with the other case with 5-cent and 4-cent stamps, we can break this into two possibilities. So two cases. Case 1. Suppose that your combination that gives you n cents includes a 5-cent stamp. So suppose the solution for P of n includes a 5-cent stamp. So you've solved, you know it's true for P of n, so there's some combination of 3s and 5s that adds up to n. Suppose in that combination you can find at least one 5-cent stamp. Okay, all we have to do is replace one 5-cent with a 3-cent and a 3-cent. Now we still have a combination of only 3-cent and 5-cent stamps, but since we took away a 5 and we added 2 3s, our total postage has gone up by 1 penny. And since we started with a solution for P of n, our combination now adds to n plus 1. So this adds to n plus 1. So if we're in case 1 and we have a solution for P of n, we can find a solution for P of n plus 1. But the other possibility is the solution for P of n includes only 3-cent stamps, no 5s. But we know that n is at least 9, and so if our combination of stamps that adds up to n contains only 3-cent stamps, we must have at least 3 3-cent stamps. Right? If we had 2, then n would only be 6. So we are using at least 3 3-cent stamps. And so here our trick is replace 3 3-cent with 2 5-cents. So take out 3 of your 3-cent stamps, put in 2 5-cent stamps. It's a valid combination. It's got only 3s and 5s, but we took away 9 cents. We added 10 cents. The total postage has gone up by 1. So this sums to n plus 1. And those are the only possible cases. Either our solution for Pn includes a 5-cent or doesn't include a 5-cent. And in either case, we found a way to write a sum of 5 and 3-cent stamps that adds to n plus 1. And therefore, P of n plus 1. Come back. Nice. So since starting with P of n, we've proved P of n plus 1, and we also proved P of 9. Therefore, P of n is true for all n bigger than or equal to 9. Does that seem reasonable? Now, the nice thing about this is it actually gives us an algorithm for finding how to make any amount of postage. Right? If you want to make 13 cents postage, all you got to do is figure out how to make 12 cents postage and then apply one of these 2 rules. And how do you make 12? Well, all you got to do is make 11 cents postage and then apply one of these rules. And we could work it forward. If you think about where this is going to lead, the first piece of actual work we're going to have to do is to make 10 cents postage. And to do that, we need to make 9 cents postage, which was our base case, which was 3, 3, and 3. And our rule was if you only have 3s, remove 3 of them and replace it with 2 5s. So this is rule 2. Get rid of those and put in a 5 and a 5. And now to make 11 cents, we take the solution for 10 cents, and first rule says if we have a 5, replace it with 2 3s. So we started with this. We replace this with a 3 and a 3. That's rule 1. And there's 11 cents. And 12 cents says if you have a 5, replace it with 2 3s. So take 5, 3, 3, replace that with a 3 and a 3. That's rule 1 again. And 13 cents, if that was our original goal, would say if you contain only 3s in your solution, take 3 of those and replace them with 2 5s. And that's rule 2. And so there's a solution for n equals 13. It's a 3 and 2 5s. But we could write a program to do this very easily. The hardest part of the program is just representing the number of 3 and 5 cent stamps. So use a pair of integers or something. But from the proof that there is a solution, we actually find an algorithm for the solution. But it's got this recursive feel to it where we're not actually solving the problem for 13 directly. We're first solving the problem for a smaller value of n, and then modulating that solution to get our final solution. Okay, that's very characteristic of recursive algorithms. So questions about that? All right, let's leave mathematics completely for a few moments. And let's see a totally different application of induction. So this is called the odd pi fight theorem. So what is an odd pi fight? So what's a pi fight? You get a bunch of people, you each have a pie in your hand, and you throw your pie at someone, right? I've never actually been in one, but I always thought it sounded cool. So, so what's an odd pie fight? Well, it's a pie fight with an odd number of people. And there's some specific rules for an odd pie fight. So one, number of people is odd. And we're going to say it's got to be bigger than or equal to 3, because you don't want to just fight with yourself. So what do? People walk into a room, and as they walk in, you hand each of them a pie. And they stand somewhere in the room, and they must remain stationary once they're ready to start the fight. So everybody goes and stands somewhere in the room, and they're holding a pie in their hand. Okay? When they've all fixed their positions and they're not going to move anymore, we need to have this second rule. Distances are unique. Distances between people are unique. What does this mean? If you pick any two people and you measure the distance between them, it's exactly 72.5 centimeters. No other two people in the room can be that exact distance apart. Okay, distances are always unique, and that's generally going to happen if you measure accurately enough. So 3 or more people, odd number of people, unique distances. And then the way the fight actually plays out is each person throws their pie at the person who is closest to them. And we can say the person because it will be a unique person who is closest to them because distances are unique. So if the closest person to me is 25 centimeters away, nobody else can be exactly 25 centimeters. Right? So we can always find the one person who's closest to each person in the room. So you got the setup, right? Everyone goes into the room, has a pie, they stand somewhere, we don't know where. And then when you say go, each person throws the pie at whoever is closest to them. Okay, so here's what the theorem says. At least one person survives, meaning doesn't get hit by a pie. They're not actually fatal. So at least one person will come away without having had a pie thrown at them. That's the odd pie fight theorem. Does that sound anything like what we've been talking about? Probably not. The what? Yeah. Maybe like the tiling problem. All right, well, we can prove this using induction. So what's a good proposition? Yeah, a room full of n people?
Sure, odd n.
Odd n, okay. So P of n can be the proposition in an n-person pie fight. There is a survivor. This is just a proposition, so we're not saying this is always true. But what we'd like to do is prove P of n for all n bigger than or equal to 3, where n is odd. So now we've got an odd pie fight. And we're going to do a slightly different version of mathematical induction. We're going to prove P of 9, and we're going to prove P of n implies, sorry, we're going to prove P of 3, and then we're going to prove P of n implies P of n plus 2. And that's going to give us P of 5, P of 7, P of 9, and P of any odd number bigger than or equal to 3. If we wanted to do this where P of n implies P of n plus 1, we'd have to talk about, instead of an n-person pi fight, something like a 2n plus 1-person pi fight. But then we're doing math, and I don't want to do math in here. So we'll just induct on the odd numbers. All right, so you know what the proposition is, right? N-person pi fight, there's a survivor. All right, well, we need a base case. So P of 3 says if you have a 3-person pi fight, there's a survivor. And let's just think about what the possible scenarios are for 3 people in a room. So let's call our people A, B, and C. And there's a distance between A and B, B and C, and A and C. So they're sitting kind of in a triangle of some shape. And all the distances are different, so we can find the smallest distance of these 3 distances, right? And let's just suppose that the smallest distance is between A and C. Well, since A is closest to C, A is going to throw their pi at C, and since C is closest to A, C is going to throw their pi at A. And it doesn't matter who B throws their pi at. Nobody's left to throw a pi at B, so B is going to survive. And we can say without loss of generality, because it doesn't matter if I call this A and B, right? The person who's not sharing that closest distance to someone is not going to get hit by a pi. So there will be a survivor for 3 people, and so we have a base case, P of 3. Okay, now suppose P of n is true, where n is bigger than or equal to 3 and n is odd. We'd like to prove P of n plus 2 is also true. So consider a room of n people, sorry, n plus 2 people. So they're all in a room, they're all holding a pi, they've got unique distances. Yes?
When we're proving the base case, do we also have to provide a scenario when A is closest to C, but B is closest to A?
Let's see. But B is, you want it closer to A than C, or do you want it closer than this distance?
Like a triangle with an obtuse angle?
I don't know if I can. You thinking like this? Stop doing that. You thinking like that? Yeah, so so in that case, A and B are going to be closest to each other. They'll throw their pies to one another. Yeah, I know, it flips around. And to do this rigorously, right, we'd probably want to lay out all possibilities using A, B, and C, but here we're just going to wave our hands and say without loss of generality, this is always true. Okay, so now we have n plus 2 people in the room. Okay, pick the 2 people closest to each other. And let me just call them A and B. So we've got A and B, and then we've got some other group of all the other people, which is n people. A and B are the two people who are closest to each other. All right, so everybody gets a pie. They're standing in the room. You say go. Again, A is going to throw their pie at B. B is going to throw their pie at A. Agreed? Because they're closest to each other. So now, in this other group of people, we have n people and we have n pies. And there's two possibilities. Case one, someone here throws their pie at A or B. So somebody in this remaining group of n people with n pies throws their pie at either A or B. Okay, that's one possibility. And in that case, after that person throws, you're going to have in this group n people who haven't been hit by a pie yet and only n minus 1 pies. And it doesn't matter who throws their pies at whom. If you only have n minus 1 pies and you have n people, it's not possible that everybody gets hit by a pie. And so someone survives. All right, case two, nobody here throws their pie at A or B. So you have n people, you have n pies, and they're all throwing their pies at each other, and they all have unique distances. What is that? Yeah, that's an n-person odd pie fight, right? And so by P of n, someone survives. Right, because we're supposing P of n is true, and by P of n, somebody's going to survive that scenario. And those are the only two possible cases. Either someone here throws their pie at A or B, or nobody in there throws their pie at A or B. And in either case, there is a survivor. And so we've shown that in any setup of n plus 2 people, someone survives, and therefore P of n plus 2 is true. And therefore, by mathematical induction, P of n is true for all n bigger than or equal to 3 and odd. So questions about that? All right, well, let's keep going with non-mathematical applications. So theorem, in a field containing, I don't know why it keeps doing that, containing n horses, n bigger than or equal to 1, all those horses are the same color. All right, in a field containing n horses, all those horses in the field will have the same color. And we're going to prove this using mathematical induction. And that should bother you because not all horses are the same color. There's brown horses, there's white horses, there's black horses, there's striped horses called zebras, and there's purple horses called unicorns. So we should not be able to prove this theorem, but we're going to prove it using mathematical induction. All right, so we need a proposition. So let P of n be the proposition. In a field of n horses, all are the same color. And we'd like to prove this is true for all n bigger than or equal to 1. So we can take 50 horses, put them out in the parking lot, and they're all going to be the same color, no matter where we get these horses from. All right, well, what does P of 1 say? It says if you have a field containing one horse, every horse in that field will have the same color. And that's clearly true, right? If there's one brown horse, every horse in the field is brown. So P of 1 is certainly true. If there's one red horse, every horse in the field is red. So P of 1 is true. So P of 1 is definitely true. All right, let's assume P of n. So just suppose for a moment that we know that this ridiculous theorem is true for some n. If you have 5 horses in a field, they're all the same color. Then we can very easily prove P of n plus 1. So how do we do this? Consider n plus 1 horses. So let me name these horses h1, h2, hn minus 1, hn plus 1. Those are great names. They all look alike, so you got to have like a way to tell them apart. All right, so there's our n plus 1 horses. We want to prove they're all the same color. Well, we can do the following. Consider the first n of those horses. Here we have n horses, and we know that P of n is true. Therefore, all are the same color. But we can also consider these n horses. And there we have n horses. And P of n is true. And so all of these horses in that second box are the same color. Well, suppose all the horses in this first box were brown. All of these horses in particular must be brown. And since those horses are in the second box, every horse in the second box must also be brown, which means hn plus 1 is brown. So all n plus 1 horses are brown. Therefore, all n plus 1 horses are the same color. Therefore, P of n plus 1 is true. And therefore, by mathematical induction, P of n for all n bigger than or equal to 1. So all horses must be the same color. So what the heck's going on here? What did we do?
Something's funky with your assumption that P of n is true. Can you go back to your previous example? You also assumed that P of n.
The odd pie fight? Yeah.
Assume P of n is true, P of n plus 1.
Mm-hmm. Right, and when I write what P of n is, we're not saying whether that's true or false. We're not making any claim that P of n itself is always true or false or neither, right? We're simply saying if P of n is true, can we show, in this case, P of n plus 2 is true, right? In the case of the horses, we're not claiming P of n is always true, but we're saying, suppose P of n is true, make your logical argument and conclude that P of n plus 1 is also true. But that, together with the base case, gives you that P of n is always true. So something's fishy here.
If you go from P of 1, P of 2, then there would be no overlap between these sets.
All right. That's the quickest that any class has ever figured this out. So I snuck this past you, almost. When you have a problem like this, right, start looking at specifics, right? We know that this should not be true in general, so let's take a particular example and see if we can break it down. So if we suppose P of 4 is true. That would mean any 4 horses are the same color, right? So let's just suppose our 4 horses are brown, 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 brown. Okay, if I have 5 horses, what is our proof saying? It's saying these 4 have to be the same color. Come back. These 4 have to be the same color. Wait. I'm plugged in. This is a feature. All right, if we look at 5 horses, we're saying these 4 are the same color because P of 4. And we're also saying these 4 are the same color, right? So if this was brown and brown and brown and brown, well, since these 4 have to be the same color, this one has to be brown also, right? But in the case of 2 horses, we have a problem. Because we're saying, take this collection of horses, all of those are the same color, that's P of 1, that's true. And take this subset, all of those are the same color, that's true. But we're assuming that, as you said, there's an overlap. And that's what makes the things in this set and the things in this set the same color. But in the case of n equals 2, there is no overlap. So this argument that P of n implies P of n does not work in the particular case where n equals 1. Right? And even though we have a good base case P of 1, P of n implies P of n plus 1. This is only for n bigger than or equal to 2. And if we knew that this was true for 2, if we had P of 2, then we could take 3 horses and we'd be done. We'd know that these 2 had to be the same color, say brown, and then we'd know these 2 had to be the same color, and that would make this one brown, and then we've got P of 3. But in this case, we picked a base case that doesn't allow us to go from n to n plus 1, where n is that value in the base case. So the moral of the story is, 1, you got to be really careful when you pick your base case. It's not always n equals 1. And you got to make sure that when you're doing your proof that P of n implies P of n plus 1, you're not sneaking something in there that works in most cases, but not necessarily in the base case. All right, cool. That was nice. That was fast. So yeah, this one was pretty subtle. So questions, comments about that one? All right, you're really bored and you're waiting for a bus or something and you've got nothing to entertain you except a calculator, so you start adding numbers. And you say 1 plus 1 plus 1 and you get 3. And you say 1 plus 1 plus 1 plus 1 plus 1 and you get 5. And you formulate this incredible theorem that if you do 1 plus 1 plus 1 n times, you're going to end up with n. You're inventing multiplication. So n ones added together should give you n. But you'd like to prove that this is true for all n bigger than or equal to 1. And unless you have some way of saying this is just n times 1, which we've never actually proven for an arbitrary number of terms, right? This is fairly obvious but fairly difficult to prove unless you use induction. So this is a really cool problem to try to prove rigorously because it's so glaringly obvious to us that 1 plus 1 plus 1 100 times is going to be equal to 100, that to be able to somehow get away from that obviousness and put together a formal proof, it can be a big challenge, right? So let's make a proposition. So let P of n be the proposition. And I'll use a summation. Sum from I equals 1 to n of 1 is equal to n. So P of 1 just says 1 equals 1. And that's true. So we do have a base case. Well, how can we prove that if P of n is true, then P of n plus 1 is true? And I'll let you use something that you already did in a homework problem or something we went over in class when we talked about summations, which was sum from I equals a to b of something plus the sum from b to c of something equals the sum from a to c. In other words, you can break these summations up into two smaller summations as long as this one ends where this one begins. Sorry, that should be plus 1. So this can go from a to b, this can go from b plus 1 to c. So we can write the following. Sum from I equals 1 to n plus 1. Well, that's n plus 1 ones, right? This is just n ones plus an extra 1. That's just properties of the summation symbol. So if I want to add n plus 1s, it's the same thing as adding n 1s and then adding one more. Everyone agree with that? So let's suppose P of n is true. Well, if P of n is true, what is this summation equal to? It's equal to n, because P of n says that summation from 1 to n of 1 is equal to n. And so that summation from 1 to n plus 1 is equal to n plus 1. And that's exactly what P of n plus 1 says. Therefore, P of n for all n bigger than or equal to 1 by mathematical induction. So that's a kind of classic example of we understand this intuitively, right? How would we prove this to our friends in an informal way? We'd say, well, just add up the first n ones and you get to n, and then add one more, you're going to get n plus 1. It's obvious, right? If adding 100 ones gives you 100, if I add one more, it's going to give me 100 plus 1, right? But then your friend can say, well, what about if you had 200 ones? And you roll your eyes and you say 201 gives you 200, and if you add one more, you get 201. And they say, what if you have 300 ones, right? So what this is doing is it's letting you generalize from the specific cases where you can prove this for 2 or 10 or 100 or 1,000 to the general case where you can prove it for any n, right? That leap from the general to, from the specific cases to the general, that's what mathematical induction is doing for us. Okay, at some level, that's always what it's doing for us. It's letting us take this intuition that we don't have to do this for this particular number. We could have used a different number, and it still would have gotten us the same result. Right? Well, this lets us formalize that, and this proof of the inductive step is the description of how you get from n to n plus 1 in general, not just for n equals 10 or 20 or 100. Yeah. Yeah, you can use induction for lots of stuff. So we know this rule from 250 digital logic, right? This is De Morgan's theorem. A and B complemented is the complement of A or the complement of B. And let me write this in a different form. So A1, A2 bar equals A1 bar or A2 bar. So same statement, I'm just using different variables. We also have a 3-variable version of De Morgan's theorem. Bless you. All right, this works for 3 variables as well. And how could we prove this? Well, given this, can we prove this? Because this is really the form of De Morgan's theorem that we usually present and cling to and use for everything. But have you ever proven this 3-variable version of De Morgan's theorem? Anybody proven it? I don't think we do it in 250. Well, so I can throw a bar over both sides and make this left side positive. A1 and A2 is the complement of A1 bar or A2 bar. I don't even need to do that. Let's just use a different form of De Morgan's theorem, right? A1 is anything, right? So anything ANDed with anything, complement is just the OR of those complements. Well, I can think of one of my terms as A1, A2. Let me do it differently. I'll do that. Think of one of my terms as A1, A2, and think of my second term as A3. This is something ANDed with something else. And if I complement that, De Morgan's theorem tells me that I should get the complement of the first thing ORed with the complement of the second thing. That's just De Morgan's theorem on 2 things, right? But now I can use De Morgan's theorem again on this and say that this is equal to A1 bar or A2 bar and leave A3 bar as is. And suddenly we've got De Morgan's theorem on 3 variables. And we just keep doing this for n variables. So we now know A1, A2, A3 bar equals A1 bar or A2 bar or A3 bar. And so if we take this as one variable and this as a second variable and we AND them and we complement, our 2-element De Morgan's theorem tells us we should get the complement of the first ORed with the complement of the second. And now this 3-element version of De Morgan's theorem tells us that this term is equal to A1 bar or A2 bar or A3 bar. And we leave A4 bar as is, and there's our 4-variable version of De Morgan's theorem. And there's nothing magic about this that would make it impossible to go from 4 to 5. We're pretty confident, at least if we do this 1 or 2 more times, that we could go from here to 5 variables using the exact same approach. And we could go from 5 variables to 6 variables using the same approach. And we believe, after doing this, that if we wanted to prove this for 100 variables, we could do it. It would just take 98 steps to go from the 2-variable version up to the 100-variable version. But then what if you want to show it for 200 or 2,000 or 2 billion variables? Right? You don't want to go through all those steps. So we can throw an inductive proof at this and generalize this process that we're using to get from n variables to n plus 1 variables. So think about that. We'll run through the details of that tomorrow. And then we're going to talk about a very old puzzle called Towers of Hanoi. All right, I'll see you next time.